Recording is rolling. It is Thursday, November 7th. Here's what I'm going to do today. So I've got a few more posters I'm going to go through. We'll finish those up. It'll take me a few minutes. Then on your desk is a lab page. Right, you guys see Pendulum Speed Lab right here. All right, so talked about this a little bit last couple of days. I'll do a quick review with you guys and show you guys what to do. Right, and then on the back, guys, the back of that paper is blank because I want to have you guys do a derivation there. Okay. All right, so homework assignments. You guys got your planner out. You guys remember that 3-page table we've been working on? Have that finished by, I think tomorrow. I want to try to finish that with you guys. All right, so have that finished. On Google Classroom, I'm going to post a link to, do you guys know a YouTube channel, Mark Rober? You guys know Mark Rober? Right. So he has a Pinewood Derby video. Do you guys know a little Pinewood Derby car? It's about like it's about this big. Right. So you get in a box, like a block of wood, some wheels, and yeah, he shows exactly how to like make the best car just using physics, and then he has like some scientific data to back it up too. Right. And it's exactly the stuff we're talking about with conservation of energy. It does a really nice demonstration. So I'll post that link over the guys sometime over the next few days. I really encourage you guys to watch that video. Right. Right. And then you guys' progress check. That's been open a few days. I read the questions and we've covered almost all the content. In fact, the stuff I haven't covered, I'll probably cover in the next few minutes. So you guys be working on those. You guys have done a few of these. You guys know if you just do a few questions every day, then that's not a big deal. You can knock those out. All right. And then I want to go over those answers to that on Wednesday, I think. Right. Because there's no school Monday. There's FCLE on Tuesday. Oh, and speaking of FCLE on Tuesday, my first 4 classes are being relocated. Here's this. And then, guys, I did post a Google Classroom an Excel file that says exactly where you're testing, if you're testing. And I think a lot of you guys are testing. Okay. So it's on Tuesday, the FCLE, Florida Civics Literacy Exam, I think it's probably. Right. Right. So anyway, there's a file on Google Classroom, shows exactly who's testing and otherwise where relocations are. Okay. All right. So you guys get there on that? All right, so let's take a look at these posters because spent the last couple of days doing some posters each day, but there's just a few more I got to go through. Right. So this one I'm gonna circle back to when I get you guys started on your lab. This is gonna be your guys' lab today, so I'm gonna come back to that one. Right. So hang tight there. All right. So let's look at some Atwoods. Atwoods. Now you guys know Atwood. You guys did a whole Atwood lab a few weeks ago. You guys remember there was the classic Atwood double elevator, and then you guys did some of the kind of like more like this. Really, it's like the modified version, right? Now, a few weeks ago, guys, what I had you guys try to figure out was what's the acceleration based on these masses. Right? So as you swap out these masses, right, one has the downward acceleration, one is going upward, but they have the same magnitude acceleration, right? And then I show you guys how to solve it on paper. Now that's a skill that you need to have, right? Now the question after that could be like, after so much time, how far has it moved? Or after so much time, how fast did each move in? Like that could be a good kinematic follow-up question, right? Or how about this? After some distance moved, what's the speed? That could also be something you can know if you know the acceleration, right? Right. But guess what? You can answer that exact question also with this conservation of energy method. And it goes like this. Here, guys, I'm just showing you guys the big picture, like how to think about this. And then you're going to get like textbook puzzles and very likely AP questions that exactly this. Obviously that's why I'm showing you. So this is how you think about this. Is that, guys, this M2 is heavier, right? So isn't it going to fall down? Isn't that supplying in essence a type of energy? What type of energy is it supplying? The fact that it can fall? Gravitational potential. And that's why I put here in green. So the sum of energy initial, here's your framework. So the sum of energy initial is just the fact that the large block M2 can fall some distance h. Is that? Right. Right. This is for the M1, M2 Earth system. Right. Conservation of energy. Right. Now, guys, that energy goes to 3 places. 3 places here. Something plus something plus something. Guys, what's one place where the energy goes? Into? Oh, okay, kinetic. Now, guys, does each block have a kinetic energy at the end of this motion? Yep. So that's this 1/2 mv squared plus also this other 1/2 mv squared, right? Different masses, right? Right. Notice, notice, guys, v could just be the speed. I don't care about the fact that one's moving up, one's moving down. I don't care about directions for this section, right? So it doesn't matter if it's moving up, down, to the side. All you care about is the magnitude, so the speed, right? So you can just plus, okay? Okay. But I'm covering up one more term. Guys, what's the one term I'm covering up? Aha! Yeah, you have to lift the small block. So some of the energy goes into lifting the small block. That's why I put M1GH on the Okay, is it? Okay. Now, do you guys see, guys, there is an optimal question that comes out of this process. And the question goes like this. What is the end speed based on this distance change? Okay. Now, you could solve that with the old method. You could do, I'm going to solve for acceleration and then go back to kinemagnetic motion. You guys remember that bridge from dynamics to kinematics? You could do that. Or you could solve it a lot faster this way. Like yesterday, you guys remember car braking to a stop? We solved it both ways, got the same answer. So same thing here. Now you have an option how to solve it. But this way you solve it faster. So if you ever see that question, like how fast does each block move in after it moves like 40 centimeters, this is a really good method to do that. Okay. Right, here's a little bit different setup, right? But it's the same thought process. Like, okay, this heavy one over here can fall. Right, so that's like supplying the energy. So sum of energy initial, right? This large block can fall, right? That energy is going to go into, in this case, 4 places. It has to lift the small block, right? So there's the mg's lifting the small block. And then each of these 3 blocks is going to have a speed, therefore a kinetic energy. So 1/2 mv squared term for each block, okay? There's some number of joules here, joules. Right? Now, one more detail. How about this top block here? If it's on wheels, then you can just ignore all this orange text if it's on wheels or if it's an air hockey table. But guys, if it's sliding, like if there's friction, right? Which actually put here because one of your college physics questions has friction on top. It looks just like this and there's friction. Okay. Wouldn't you have to subtract out the work done by friction? Okay. So think about this being like an open system. Okay. Versus kind of like the car braking to a stop. You guys see that? Okay. All right. There you go. So friction force times distance. Check that out. Okay. I have a few posters for mechanical advantage. This is one of the labs I'll have you probably next week. I'm thinking I want to have you guys do this lab. You guys see pulley system here. All right. So guys, here's the guiding principle: it's conservation of energy. So work input equals work output. So if I'm pulling on this end of the pulley, it's going to lift this weight. Right? And you guys see that right in front of me in class. I can pull on this end. It's going to lift this weight. Right? Now, turns out you can get what's called a mechanical advantage. You can put a really tiny input force and lift something that's very heavy. Now, you pay for that in distance. So the catch is you have to pull lots and lots and lots of distance to pull this up only a little distance at a time. You guys see different distances going on, right? Based on the geometry of the system. Right. So do you guys see like 3 strings effectively pulling up this one large weight? Of course, it's the same string, but from the point of view of this weight, it looks like 3 different strings, doesn't it? Right. So it's kind of like the weight gets split 3 different ways. See if you guys are following. Guys, if this thing weighs 30 newtons, how much force do you think I have to pull with over here? 10. That's called a 3-to-1 mechanical advantage. I've amplified my strength by a factor of 3. Now you can amplify your strength. Can you amplify the amount of energy in the system? No. Right. So it doesn't multiply energy. It can multiply force. Right? Here's ideal mechanical advantage. It's just the ratio of the distances. You can get that from the geometry. Then there's called actual mechanical advantage. Do you think realistically there's probably like a little bit of frictional loss here? It's not exactly 3-to-1. You have to pull a little bit harder. Yeah. Okay. So you take that ratio. It's probably something a little different. Right. And then you can take the ratio of these ratios and get something called efficiency. All right. I'll have you guys do that lab. Oh, look at that. Look, got a lab page right here, all ready to go. That. There's different ways you get mechanical advantage. You can do it with wheels, right? So what if you have a small wheel and a big wheel like fixed in place relative to those? They're locked in place. They're both moving. Hey, that looks like a kind of like leverage. Ooh, get a 3-to-1 mechanical advantage. Right, something like that. Hey guys, do you ever get a box that's way too heavy to lift? Maybe it's just barely too heavy to lift. It's like I can't lift this block. Right? But maybe I put it on wheels and I got an incline, kind of just push it up the incline, right? You can get a mechanical advantage this way. These are all different ways to get a mechanical advantage. So a little bit different perspectives. Okay, got a pulley system. We got the wheels, leverage. We got the incline. Right. Okay. It ends up being this is push divided by this height change, just the mechanical advantage. Okay. Here's a full list of simple machines. If you open up any science textbook and go to simple machines, it'll give you this list right here. Here's all the simple machines. I showed you guys that one. Kind of these two were kind of similar. You guys saw the incline plane. Okay. Those. Okay, also we got here's possibly a lab version I might have you guys do. Okay. All right, new stuff. Power. Guys, I barely talked about power yet. Guys, what was the unit was power measured in? Watts. That's right. And 1 watt is equal to 1 watt per what? Joule per second. That's work over time. Yeah, joule per second. So power is a rate of energy transfer, which is a rate of work, right? Work over time, right? So that could be joules per second. That could be watts. If you look on a light bulb, so it's 40 watts. It's drawing 40 joules per second, say off the grid, something like that. Right. Now, here, I want to do something kind of funny with this. Guys, work is what times what? Force times distance. That's right. and time, I can call it like t, right? Okay. Do you guys see that this and this are the same thing, right? You guys see it? Right. Now, what if I wrote these two variables together? Guys, distance over time, what does that call? Speed. Aha. Right. So, guys, if you have an elevator that's being pulled up by, say, some tension force, okay, that could be the force. And let's say it's going at some speed, right? Do you guys think there's like some motor at the top of the elevator shaft pulling up this elevator, maybe some number of watts, like 3,000 watts or something, right? Oh, that's how you can calculate it. Just say, what's the force it's pulling with? And then how fast is it going? Boom, boom, done. That's it. Right? Now, guys, if it's going constant speed, then what do you know about this tension force compared to this weight? Equal. Right? Equal, right? And if it's not constant speed, if it's accelerating, then maybe you have to do the m times g plus a, maybe something like that. Okay, great. Wait, I've seen AP ask exactly that question in the past, where it's accelerating. You have to do, well, tension force is actually m times g plus a, right, and then solve that way. Okay, so that was a little bit different force. Okay. All right, we're getting down here near the end. Just got a couple more to show you guys. All right, do you guys remember? Ooh, let me go back to this page here. For potential energy, we've just been doing MGH, gravitational potential energy, MGH. Right. Well, if you're sending a rocket to the moon, you really have to use this universal form here, this green one, right? And also, that's a challenge question, guys. I think the very last question on your energy packet, that table, involves two asteroids gravitationally attracting. You have to use this form. We'll possibly go over that tomorrow and then see if you guys got the right answer. Okay. But I want to show you guys something. I want to show you guys that if you have a small change in height, say if you go from the top of Mount Everest to sea level, right? I know this sounds like a big change in height, but that's small relative to the radius of the Earth. That this simplifies to just MGH. Right? Now just look at the form, like GMM over R. Doesn't that look kind of like GMM over R squared, which was a force? Force times distance could be like work, right? If the distance is like R, one of the R's cancels, right? Okay, so that looks plausibly true, right? Now watch this. If I go through this process, what if you go from the top of this tower to the bottom of this tower? So in terms of radial changes, that R2 minus R1 could be the height change, right? You see height is R2 minus R1. Let's go through this. So the change in potential energy from the top of the bottom of the tower, it's just I'm subtracting those two potential energies, and the only difference is the R down here. It's R2 versus R1. You guys see that? Right. So next step. Ooh, guys, minus a negative. Could that be like plus a positive? Okay. Now if I get common denominator, can I multiply this top and bottom by R1 over R1, this top and bottom by R2 over R2? Slip that in right there. Okay. Now I get a common denominator of R1 times R2, right? And I can factor this out in the top. You guys see that? Right. Now one last thing. As long as the difference is if this height is very small compared to these radial values, is R1 approximately equal to R2? Approximately true, right? Approximately true. So that makes this R1, R2 equal to just basically R squared, right? Is that basically R squared? Right. And then this R1, R2 minus R1, could that just be H, right? That could be H, right? Okay, so in place of this R2 minus R1, I'm going to call that H, right? This M is just going to be whatever mass that you drop the ball off the tower, right? And then here in brown, you have GM over R squared. Hey, GM over R squared, what is that? That's gravity field. Hey, oh, look at there. It's MGH. You guys see MGH? Aha. Right? So as long as you're basically at the surface of a planet, you're allowed to use MGH, right? Which is what we use like almost all the time anyway. Okay? All right. One last detail. I'm going to take this universal form of gravity, and I need to prove to you guys escape speed. Right? You guys ready for this? All right. So this one you have to think pretty abstractly, but here's how we're going to go. Let's say there's a big old universe with nothing in it except for I have a planet here in my left hand. This is a planet. And on the complete opposite end of the universe, I have a little tiny mass, maybe a little tiny rock. Right? You guys said that? Right? And do you guys think they feel a tiny, tiny, tiny gravitational attraction? Right? Do you think after maybe like a billion years, this tiny these two gravitational attract and bam, stick together? Right? But if the planet's like crazy, crazy bigger than this little tiny rock, the planet hardly moves. Maybe the rock just comes crashing into it, right? From the edge of space. Right. Okay. Well, guys, if it crossed the universe, it took a billion years to finally, bam, crashes into it. Oh, how fast is that crash speed going to be? Is it going to be infinitely fast? No. Is it going to be like the speed of light? No, nowhere close. Right. I'll show you guys what that speed's going to be. So think about it like this. They start at the edge of space. Do they have any kinetic energy if they're just starting to rest? No, zero kinetic energy. Right. I'm also going to do this. I'm going to define all the energy as zero. Right. Did you guys notice universal gravitational potential energy? It's like a negative value. You guys see it's like a negative value, right? So as they fall closer to each other, isn't the gravitational energy potential energy decreasing, getting smaller, 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 right? course, it's like it's falling. Right? So it starts at 0 and it only becomes negative after that. Okay. Right. So by the time they crash together, I bet this one has a lot of kinetic energy. But where did it get that from? It got that from the potential energy. Here's the universal form, negative GMM on R. Right. Right. And but it still has to zero out because there was zero energy to start with. So there's zero energy to end with. It's just a positive kinetic and a negative potential. Okay. Right. Now you can solve for this V. Do you guys see the mass of the rock from the edge of space is going to cancel out? Right. You can solve for this V. And if you do, you get this speed. This is the crash speed of something that comes from the edge of space. This is how fast it's going to crash into the planet. It's simple. Right. What that means, though, then, is if you want to fire a rocket and get it going to a speed so that you can cut off the engines and it goes back to the edge of space, well, that's I'm describing escape speed, right? That would also be the same speed from the surface of the planet. You got to get going this fast. You just got to get aimed away from the planet. All right, so there you go. There's where escape speed comes from. All right. There's all the posters. There's all the posters I got to do with you guys. All right, so let's do today's lab. All right, you guys got right, well, here's what you want to do. Right. So now you guys, AP, we're gonna have you guys do this. Right. So the lab right here. Remember what you're trying to find is what's the speed at the bottom. I'm gonna have you guys calculate it using this. Actually, you're gonna derive it. And then also you guys got those speed gates, right? Got these little speed gates. Right? You guys think you can turn this upside down and have the way go zoom through it and read exactly what the speed is? Right? All right. So that's an empirical measurement. Okay, so there's a calculation column for speed, and there's also a measurement column for speed. I wonder if they're going to be the same thing. Okay, guys, do this. Flip your lab page over, and on the back, do this. Do sum of energy at the top equals sum of energy at the bottom. Right, you guys got that? Right. Now, what I want you guys to do here is make believe that right now you guys are getting a free response question on the AP exam, and they're asking you, what is the speed of the pendulum at the bottom? And they want you to solve it in terms of variables. And this is your free response question. Okay. And the answer is right here, guys. All I want you to do is, except I did skip a few algebra steps. So show all the algebra steps I skipped. Right? But see if you guys can come up with this like from scratch. So like it's test time. I got to be able to do this. Oh, I remember that was one of those posters. Right? And here's going to be ultimately the answer. Ignore the gray ink because you're not giving it a push. You're just really seeing it from rest, right? So don't do the gray ink. Don't worry about that, right? But see if you can figure out what is. You're going to have a bunch of steps here. I'm skip. And at the end of this page, you're going to have v equals, and it's going to be a square root. And well, you can get the answer. Okay. All right. So I'm going to leave this up here. Go ahead, take the rest of class. Try out different masses. You guys have different masses on your desk. You guys have some string and some scissors. You guys have a protractor on your desk. You measure this angle. Right? You can calculate the speed because you're about to derive it yourself. And you can measure it. And hopefully they're the same thing. All right, go ahead. And then just turn this into the gray tray at the end of class.